This video was brought to you by GeneralPack.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/generalpack. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Introduction to Power Factor Part 2b. In the previous part, we had a look at a general overview of the concept behind power factor, and we used a phasor diagram to understand the relationship between the voltage and current in an AC circuit. In this part, we will be using the previously established knowledge to construct a power triangle, which will allow us to understand the relationships between the three types of power and the power factor. Recalling the previous parts and building upon the beer or drink concept, the power triangle is simply a right-angled triangle which shows a relationship between three types of power using simple trigonometry. We shall first draw the real power component and establish the relationships from there. We know that the real power is considered to be the actual work done without any losses. Therefore, its magnitude is a real value in terms of watts, and its angle is taken as 0 due to no losses. Drawing this as a vector, we get the real power as a straight line. This indicates real power. Next, we saw that the reactive power is required by induction loads for generating the magnetic flux. The reactive power causes the angle to shift between 0 and 90 degrees and is relative to the amount of the magnetizing flux required by the inductive load. In a purely resistive circuit, the angle will be 0 due to no magnetic flux requirement. But in a purely reactive load, the angle will shoot up to a maximum of 90 degrees. For our case, let us consider a purely reactive load, and therefore we shall draw the reactive power as a perpendicular line to the real power. Finally, as discussed in the previous parts, the apparent power is the vector summation of the real and the reactive power. Therefore, we shall add both components vectorially in a form of a hypotenuse. This indicates the apparent power. We can recall the fact that the current flowing in an AC circuit has two separate rectangular components in a form of a cosine and sine component. If we want to model the component mathematically, the real power, denoted as P, will be the product of the voltage and the active component of the current. And by multiplying by the cosine of the angle, we effectively get the horizontal or adjacent line of a right triangle. So real power, which is P, is equal to V times I times the cosine of the angle. Similarly, the reactive power, denoted as Q, will be the product of the voltage and the reactive component of the current. By multiplying with the sine of the angle, we effectively get the vertical or opposite line of the right triangle. So reactive power, or Q, is equal to voltage times current times sine of the angle. Next, we apply the well-known Pythagorean theorem to calculate the apparent power. Thus, the apparent power, denoted as S, comes out to be the product of the magnitude of the voltage and current. This effectively gives us the hypotenuse of a right triangle. So apparent power is equal to S, which is equal to voltage times current. Finally, we can see from the right triangle that there exists a phase angle between the apparent power and the active power. We know that the power factor is a measure of how effectively we are using electricity and equals the cosine of this phase angle. The greater the power factor, the lesser the phase angle, and hence less reactive power is present in the circuit, and vice versa. Therefore, we want the phase angle to be as small as possible in order for us to get a higher power factor. However, that is not always the case, as a practical power factor consists of loads requiring reactive power as well. In part 3, we will see some of the underlying reasons behind low power factors and the benefits which we can gain from improving it. We hope you have a continued interest in this topic and series as a student or professional, and we also hope you find this content useful and enlightening. Please consider subscribing to GeneralPack.com and becoming our patron at patreon.com/GeneralPack.